Greetings. Welcome to section 2.2, the inverse of a matrix. You may recall from previous math courses that a multiplicative inverse, for example, would be 5 times 1/5. So 1/5 is the multiplicative inverse of 5 because when you multiply those, it results in 1. Now 1/5 can be written a different way. Remember that 1/5 is the same thing as saying 5 to the negative power of 1, which is also the notation for an inverse. This is also equal to 1. So this is notation, and when we are dealing with matrices, we are going to use this notation here. So when we are dealing with the inverse of a matrix, we must have square matrices. So it must be an n by n matrix, and we will say that matrix A is invertible, and this phrase is going to come up again. It is invertible if there is another square matrix C such that C times A equals I and A times C equals I. Now remember, I is the identity matrix, and matrix. And that identity matrix, remember, it's ones at the diagonal and zeros everywhere else. So typically we will be dealing with the 2 by 2 and the 3 by 3 identity matrices. Okay, now both of these things must hold true. And if that is the case, then we will say that C is an inverse of A. So remember that the notation that we will deal with is this here. Okay. So first, we will have this example here where we have two matrices, A and C, and we want to determine if matrix C is an inverse of A. So what we want to do here is we want to find A times C, and then we want to find C times A, and both of these need to equal the identity matrix, so the ones at a diagonal and zeros everywhere else. So when I set this up, I have the following. And in the previous section, we dealt with multiplying matrices. So remember, it's rows times columns. And when you multiply this out from your experience in the previous section, you do, in fact, get the identity matrix here. So let's do the same type of thing and find C times A. When we find C times A, set up in this way, we take the rows times the columns, and if you do this algebra, you will in fact get the identity matrix once again. Since both of these are true, then we can conclude that C is the inverse of A. Here, we just kind of talk a little bit about notation. Again, this is solely notation. It does not mean this. Okay, so it is just the inverse. So when we're dealing with matrices, we do not do division. There's no division of matrices. So this simply means the inverse. Okay. Sometimes we will want to find the inverse for a 2 by 2 matrix. And there is a simple formula here which is stated in Theorem 4. So if you want to find the inverse of a 2 by 2 matrix, this is the formula you will use. Now, here's basically what is happening. When you are setting this up, this here is referred to as the determinant. Okay, so that's something that you may have talked about in a previous algebra class. That's known as the determinant, and it is simply A times D minus B times C. Make sure that you use a minus sign here. Okay, then to get this new and improved matrix, what we do is we flip-flop the order of A and D, and then we negate B and C. And then we perform that scalar multiplication, and we will end up with the inverse of matrix A. So let's see how this works. So here we have a simple 2 by 2 matrix, and we want to find the inverse. So it also tells us to verify that it is the inverse. So let's go ahead and get started first by finding the inverse. So from the formula in Theorem 4 on the previous slide, A inverse is found by taking 1 over the determinant, and the determinant is 2 times 4 in this case, minus 5 times 3, times the new and improved matrix. So we are going to change the order of these, so 4 and 2, and then we are going to negate the 5 and the 3. Then we simplify and perform scalar multiplication. So when I simplify the determinant, I end up with 1 over negative 7 times this new and improved matrix. So now scalar multiply, so everything gets multiplied by a negative 1/7, and my result is the following: negative 4/7, 5/7 in the first row, and then 3/7 and negative 2/7 down here. So if we have correctly done all of our math here, this would be the inverse. So this would be A inverse. Great. Well, now the next part is to verify that it is in fact the inverse. So to check this, remember what I need to do is take A times A inverse. It needs to be the identity matrix. And then I also need to take A inverse times A, and that also must be the identity matrix. So if I set this up for you, I would have the following. So this here is once again the identity, the inverse, I apologize. And to check this, I would take this row times this column and perform everything like we did in the previous section. And yes, this will equal the identity matrix. And the same thing holds true for this other one. So we can conclude that this is the inverse of matrix A. Go ahead and try this one on your own. So when you solved this to find the inverse, call this matrix A. So A inverse is 1 over the determinant, remember is 3 times 6 minus 4 times 5, times the new and improved matrix. So we change the order of these, and then we negate the other diagonal. So here, this ends up becoming negative 1/2 times this new and improved matrix, giving us the following. Oops, this should be a negative 3. And I'm here to tell you that yes, this is in fact the inverse, and I am not going to take the time to verify, but remember, to verify, both of these need to equal the identity matrix. Okay, great. So here we talk about how we can use an inverse to solve the equation AX equals B. So we have previously had a lot of different methods in which we could solve the equation AX equals B. Well, another means in which we can solve that equation is by using the inverse. Now, if you think about it, if I have AX equals B, to get X by itself, I can multiply by the inverse of A. And then these would cancel out, leaving me with X equals B times A inverse. Well, that's exactly what I have here. Okay, so let's take a look at what we have going on. Here I have a system of equations, and it says use the inverse of matrix A from the previous example to solve the system. Now, if you look at this here, these coefficients are the exact same thing as what we had in the previous problem. So we had this matrix in example 3, and we found the inverse of this in the previous example. So the system here that we have, so AX equals B, is the same thing as X is equal to A inverse times B. And remember, this is B. So if I set this up to solve this, X is equal to A inverse times B. So the inverse of this matrix that we found in the previous example is 3 5/2, 2 -3/2 times matrix B, which is 3 7. So I'll take this times this. That will give me, oops, once again I dropped this negative right here. So when I multiply that, I have -9 plus 14, which is 5. And then this times this, this is 15/2 minus 21/2, which is -6/2, giving me a -3. So this is the answer. Not so bad, right? All right. On this slide here, we have 3 useful facts about invertible matrices. So remember, an invertible matrix is a matrix that has an inverse, basically. Okay, so here, take a moment and read through these. Okay, now we talk about an elementary matrix. An elementary matrix is one that is obtained by performing a single row operation on an identity matrix. Now in this section, we are going to continue with row operations, and I think it would be in your best interest to try to go back to your roots a little bit, and in your homework for sure, practice using your row operations just so you don't forget how to do it. So instead of relying on a calculator on this assignment, there aren't too many questions. Try to do the row operations by hand. Okay, so in this example, I have told you that E1 is represented by this matrix, and this is matrix A, and we want to find E1 times A. So E1 times A, this is E1, and this is A. Okay, well, when we solve this, remember, so just going back to rows times columns, we take this row times this column. Since it's the first row, first column, the result goes in the first row, first column, which is here. Then you keep the first row, go to the next column. So your answer is in the first row, next column, which is 2. Then you continue with the same row, but the last column. So your answer goes in the same row, last column. Once you have used this row on all 3 columns, you move to the next row and you repeat on all 3 columns to get this resulting matrix here. Okay, so now what we're going to do is continue to analyze what is happening here. Okay, so now I have 4 different matrices, and I want to perform multiplication for in 3 different ways. First, I want to find E1 times A, then E2 times A, and then E3 times A. And once I multiply these, once I compute these, I want to analyze and compare how that new matrix relates to matrix A, and talk about those elementary row operations. So if I have E1 times A, I'm going to take this matrix times this matrix, and I'm going to take rows times columns. So I end up with A, B, C in the first row, same thing. I end up with D, E, F in the second row, same thing. But the third row gets a little fancier. I take this last row times each of these columns. And when I do, I end up with G minus 4 times A, H minus 4 times B, and I minus 4 times C. So here is my resulting matrix, and I want to compare this to matrix A. What row operations did I perform to get from this matrix, from matrix A to matrix E1A? All right, well, what I did, the only thing that has changed is this third row. So let's analyze this. Well, I took the first row and I multiplied row 1 by -4. Notice each of these. And then I added that to row 3. So on matrix A, I took -4 times row 1 plus row 3. And that's what I did. So let's do the same thing for the next matrix. So now we're going to take E2 times A. All right, I'm just going to show that to you quickly. It becomes the following: DEF, ABC, and GHI. So now when I compare this new matrix to the original matrix A, I notice that row 3 stays the same, but something happens to rows 1 and 2. Well, you might notice that I interchanged row 1 and row 2 of matrix A. So in matrix A, row 1 was interchanged with row 2. And those are the elementary row operations on matrix A. All right, let's do this final one, E3 times A. So I'm going to take this row times this column, so on and so forth, and I end up with A, B, C, D, E, F, 5G, 5H, 5I. So compare these. How are these different? Well, the only thing that changed was row 3 from matrix A. This has changed. How has it changed? Well, I have taken 5 times row 3 of matrix A. And that's the elementary row operation. Take a moment and read through this significant result. And then we'll look at another example. Okay, so here is another example, and it says find the inverse of the matrix if it exists. So this is the same E1 from the previous example. Now, from the previous example, what we want to do, since we want to find the inverse, remember we have E1 times something needs to equal I. Okay, so that something is going to be the inverse, and that's what we need to figure out. So E1 is this matrix, and we need to multiply it by some matrix, which is going to be the inverse, and that needs to equal the identity matrix. Okay, so if I look at this, in order to get from E1 to the identity matrix, the only thing that needs to change is this entry here. I need to make that entry 0. So what do I do to make that entry 0? Well, from the previous example, remember if I take the inverse, so if I take 4 times row 1 and add that to row 3, that's the additive inverse, remember, and get my new row 3, then I'm good to go. So 1, 0, 0, 0, 1, 0 times 4, 0, 1. So this is the operation that I used. You can check this. This times this will equal, like as you proceed, you will get this. So we can conclude that the inverse of E1 is shown there. Now, of course, if this matrix becomes more involved, it's going to be more difficult to come up with the inverse matrix in order for these to work. So there is an algorithm that is a lot easier than just, trying to think it through, and I'll show you that. But before I do, here is a theorem and a pretty brief proof of it. You can see the rest on page 109 if you want to see it. But ultimately, this comes down to the following result. If I want to find the inverse of a matrix, I can use my elementary row operations and transform this matrix into this matrix. Okay, so what happens is I take matrix A, I use row operations to make it the inverse, the identity matrix, and this will end up turning into its inverse. It's actually quite neat how it works. So let's take a look. Okay, so here I'm asked to find the inverse of this given matrix. Now, if I'm looking at this, I need to multiply matrix A by an inverse to get an identity matrix. And that gets kind of, confusing. And so instead, what I can do is use the previous results from that theorem, and I can take this, which is simply matrix A and the identity matrix in 1. Okay, so this is matrix A, this is matrix, or the identity matrix, okay? And what I want to do is use elementary row operations and change this. So I want AI to become IA inverse. So again, like I said previously, I'm going to take this and try to get it to be the identity matrix. All right, let's get started. Let's do some row operations. So here, remember I want my first term, let's change colors. I want this first term to be 1. Well, I can get that by interchanging row 1 and row 2. So I end up with the following. I'm very hopeful I don't make any errors in this video. If I do, I apologize and hopefully I catch it. The third row remains the same. All right, now I'm going to proceed. Let's make this smaller. Now, since I want this first part to become the identity matrix, I'm going to try to make this a 0. And the way I do that is I'm going to take -4 times row 1 plus row 3. I'm going to space this out, guys, and I'm going to come down here. Okay, so now row 1 remains the same. Row 2 remains the same. But I have a new row 3, which is 0, -3, -4, 0, -4, and 1. Now remember, I'm working towards making this the identity matrix. So now I'm going to try to make this a 0. And the way I do that is I'm going to take 3 times row 2, add it to row 3, and it becomes my new row 3. So rows 1 and 2 remain the same. And then we have a new row 3, which is the following. All right, now I am so close. I now want this to be a 1. So in order to do that, I'm going to take 1/2 times row 3, and that will become my new row 3. So 1 and 2 will stay the same. Isn't this entertaining? So I have 0, 0, 1. This is 3/2, -2, and 1/2. All right, now the last thing I have to do is make these 0. So when I do, I'm just going to make this a twofer. I'm going to take -3 times row 3 plus row 1. And then I'm going to take -2 times row 3 plus row 2. So rows 1 and 2 are going to change now. And I get the following. 1, 0, 0, -9/2, 7, negative 3 halves, 0, 1, 0, negative 2, 4, negative 1, and 0, 0, 1, 3 halves, negative 2, and 1 half. The third row stays the same. All right, now let's analyze what we have here. This is the identity matrix, which means this is the inverse of matrix A. So we have just gotten what we wanted to achieve. So I can conclude that this is the inverse. So on the next slide, I'm going to kind of show you a couple things. So therefore, A inverse is equal to, I'll just kind of write it out nicely for you, negative 9 halves, 7, negative 3 halves, negative 2, 4, negative 1, 3 halves, negative 2, and 1 half. Remember, you can check this. You want A times A inverse to equal the identity matrix, and A inverse times A to equal the identity matrix. And you certainly can do that. So remember, A is the matrix that was given to us in the original statement. A inverse is what we have here. When you multiply these, which you can certainly do on your calculator or whatever site you're using, it does equal this, and we're good to go. Okay, let's try another example here. So we have another 3 by 3 matrix, and we want to find this inverse if it exists. So remember, we're going to start with AI, and we want to convert this to the same thing that we did in the previous example. We want this to be I times A inverse. Okay, so we will set it up as follows. I feel like I should have like some elevator music in the background while I simply set up matrices. That'd be more entertaining for y'all, don't you think? I think I'm funny. Okay, so row operations. I have a 1 for my first entry, so that makes me smile. So I need these to be zeros. So I'm going to take row 1 plus row 2. And then I'm going to make this a twofer and do negative 5 times row 1 plus row 3. So rows 2 and 3 will be changed. Row 1 stays the same. Row 2 and row 3 become these here. Okay, trucking along. I want this to be a 0. So in order to make that happen, I am going to, there are a couple things you can do, but I'm going to take negative 2 times row 3 and, negative 2 times row 2 and add that to row 3 to get my new row 3. So when I do, rows 1 and 2 stay the same, but row 3 becomes the following. Now let's pause a moment here and see what's happening. Now remember, this is supposed to become the identity matrix. Okay. Now I hope you're noticing that something important is happening here. Notice that I have a last row of zeros. If I end up with a row of zeros, you may remember from previous lessons that something special is happening. In this particular case, if I have a row of zeros, this means that A does not have an inverse. So it would be absolutely pointless to proceed doing more row operations because you will never get this to become the identity matrix. So matrix A does not have an inverse, and this concludes this lesson.